Thank you for the introduction. Can you hear me well? Okay, there's still some empty seats here in the front, like 6 empty seats if somebody wants to take them. So I will talk about graphical models, focusing mainly on optimization techniques. Then there is a lecture in the afternoon, which is a probabilistic view on graphical models. So the roadmap for the first part of my talk, and then we have a short second part of the talk. So the first part of the talk, the outline is as follows. I start with a very brief introduction to graphical models. Then I talk about optimization techniques, which is the main part of the talk. Then I talk about comparison of optimization techniques and have about 15 minutes of neural networks and graphical models. It's a bit more of a high-level view of how they compare and how you can combine them in interesting ways. Okay, so who knows about graphical models? Who's heard about graphical models? Okay. Who knows what an integer linear program is? Okay. Who knows what TRWS is? Okay, good, good. That's what I roughly expected. Good. So you will learn something in the next 1.5 hours. Okay. So references for this lecture, we have, I listed a selection of books here. There's one particular one by Sebastian Nowitzin, Christoph Lampert, which I use for my teaching at Università quite heavily, which is called Structured Learning and Prediction, Computer Vision. There are also quite a lot of tutorials at recent conferences. So this is now making a difference to the previous presentation of Alison, where she mainly talked about this part here. So this is traditional machine learning. You've got input, could be an image or text, and you try to classify it or do a regression. So what graphical models are doing, they are a language to model so-called structured output predictions. Structured output prediction means you have got an input, like an image, and the output is not a single number, it's a set of numbers where there's a connection between the numbers, and this connection is important. For instance, you've got a sentence, and you want to say what is each word in the sentence. Is it a noun or a verb? Actually, one quick question, is it too loud, the microphone, or not? Or is it fine? Because for me, it's very loud. Okay. Okay. Good. So you have a noun or a verb. Probably will be depth after this presentation. So you have a noun or a verb, and also the structure between the outputs is important. For instance, the verb comes more likely after the noun. Okay. Now this is our task here to do this structured output prediction today. There are different forms of graphical models. One is the directed graphical models, which is one language for formalizing or visualizing a multivariable probability distribution. So these are three different ways to write them or to visualize them. One is directed graphical models, one is undirected graphical models, and one is so-called vector graph. And I will use mainly vector graphs, which is the most explicit representation of an undirected graphical model, as the language or the way how to visualize graphical models. You can very easily transition from undirected graphical models to vector graph both ways. It's just a different way of visualization. This one has been traditionally used for looking at dependencies and independencies in graphs, but it's for our purpose not really so important. And directed graphical models are quite often used when all of these variables have an explicit meaning, but for our purpose they're also not needed. These directed graphical models, you can also go forth and back between directed and undirected graphical models. Okay, so what's a vector graph? Let's start with an energy or optimization function, objective function. We have, in this case, 5 variables, x1 to x5. And we have different terms or factors in this objective function. Like this is a vector with 3 variables, this is with 2, with 2, with 2. And now we can visualize that. We take each variable and call it, it's an unobserved variable, so the axis, and we denote it with a circle and put an x1 in here up to x5. Okay? These are circles. Then for each factor, we do a square with a connection. So this factor here, which has 3 variables, has a square and have got 3 variables attached to this square. And this here is a factor with 2 variables, between x2 and x4, and another one x3, x5, and x3 and x4. So these pairwise factors, and these are so-called, you can also call them triple factors, or factor with 3 variables. Okay? You can define the order of a factor graph. This is the number of variables of the largest factor. So if here, for instance, in this factor graph, the order is 3. There is this factor here, which has got 3 variables involved. This is just a comment to undirected graphical models. There's a definition of a clique, which is closely related to factors, but slightly different, and I'm not going to details here. Then you can define a so-called Markov random field or conditional random field. I'm not going into details, probably the next speaker will do that. So Markov random fields means, or the Markov property stands for the fact that you essentially have factors with lower order. So that means if we were to have one factor where all of the variables are in, this is not fulfilling the Markov property, but it's fulfilling the Markov property when you've got a lot of factors which have got few variables in there. For instance, as this one here, then it fulfills the Markov property. Okay, there's one slide on connecting energies and probabilities. So typically, what we're going to do through the next 2 hours is we always minimize energies. There's one small part where we not only minimize, but we also compute marginals. But from now on, we always minimize this energy. And that corresponds to maximizing a so-called Gibbs distribution of the posterior, where we've got P of x, these are the unknown variables, given z, the observation. And you can write the Gibbs distribution in this form. We've got this one is a normalization constant to make it a proper distribution, and then exponential minus the objective function e of x. Okay? This is just a way how to write it, and this is the so-called Gibbs distribution. So here is a simple way of showing that maximizing the probability. So we compute the x star, which is maximizing the probability here. P of x should be P of x given z. You can also write it given z. So maximizing this, what we can do is we can just take the log, which is not changing the minimum because it's an increasing function here, monotonically increasing function, log. And then we take a minus, and the minus changes the max to a min. Okay, so this is the same here, minus and log of P of x. And then we can put the P of x, this equation we can put in here, so it's minus log of this thing. And then we can multiply that in. So log operation makes the multiplication a plus. So we get this part here is just some constant c. This one, the log and the x cancel out. The minus cancel out. So we get a plus energy. And that means we have a constant here, which we can forget if we minimize over x. And so we minimize arc min of the x with respect to x, which is the same as maximizing probability. Okay? Now this is a way of connecting energy minimization with computing the so-called maximum a posteriori or map estimation of an underlying Gibbs distribution. So very often when you see energy minimization graphical models, they talk about the map estimation, and this is then what it means. So it's this posterior, maximizing it, that means the computing this map estimate. Okay, here's an example of different orders. This is a 4-connected random field, Markov random field. This one is 8-connected, and this is a higher order random field. We've got one factor which is connected to all variables, and then a lot of pairwise factors. And this is how you write it. It's a sum of a neighborhood 4 connected with theta ij, xi, sorry, this has to be I, xi, xj, 8 connected, again has to be I here, and then 4 connected plus a higher order factor. Okay? Now what I want to do is to give an example why these different factor graphs are useful, for instance for image segmentation. So what we do with image segmentation with a 4 connected, then 8 connected, and then higher order, and see what could be the advantages of using such more complicated random fields. So in a 4 connected random field, the most simple one is called the Ising model for binary labeling, or Potts model for multi-labeling. That means we have, for instance, an image with some brushstrokes, uses done background brushstrokes and foreground brushstrokes. That means the unit potentials say here that the red and purple is more likely foreground and dark colors are more likely background. Then with a 4 connected, you can get this segmentation here. If you minimize this energy, globally optimal, and we're actually going to do this, I'm going to exactly describe the algorithm, how to do it. And this is the result you get. If you zoom in into the details, you see, for instance, this edge here is a quite sharp corner. So, and we now look into why that is, this sharp corner, and then we try to find ways how to prevent these sharp corners at segmentations. Okay, so first of all, let's look at this here, this called Ising model. What it's doing is, it's saying if 2 pixels xi, xj are connected, I pay a penalty if they're different. If this one is, for instance, 1 and this is 0, or the other way around, you pay a penalty of 1. If they are the same, if they're 0, 0 or 1, 1, you don't pay a penalty. So therefore, what this is doing here is I'm explicitly making it compact. Without this term here, you would have a lot of isolated dots everywhere, like holes in here and isolated areas here. So what's this doing is it's making it compact, and that's called the Ising prior. Okay, so why do you have these called metrication artifact, these sharp corners as are shown here? So you think about the following. You have got 2 possible lines. So this square has got length 1, let's say. So this blue line has got length 8. It's 1, 2, 3, 4, 1, 2, 3, 4. And this line here, its Euclidean length is 5.65. Okay. First of all, we don't have such lines when we go for a discretized segmentation. We have such an edge here which goes along these between the pixel boundaries along here, for instance. So the goal is when we set the weights for this one here, like for these pairwise factors. So I'm just going back here. So what I'm also, you can put some weight here, for instance, some weight in front of this Ising prior. Then if we do that and we have a 4 connected grid, you can't distinguish between length of this one here and length of this one here. So in a 4 connected grid, the number of edges which you cut on this one is the same as this one here. So you have, if you have 4 connected grid, you cut this one 1, 2, 3, 4, 5, 6, 7, 8. And this one you also cut 1, 2, 3, 4, 5, 6, 7, 8. You also cut it 8 times. Hence, whatever weight you put on this Ising prior, on the pairwise term, you can't distinguish. So this one here and this one, you have the same length. When you now go to an 8 connected, it's no longer true. You have to think it yourself a bit through, but what you see is that this edge here goes diagonal down, and it cuts few of these edges. It doesn't cut these edges here, whereas the blue one will cut a lot of these diagonal ones. And basically what you can show is that when you go to 8 connected and you put certain weights on this Ising prior, you can go closer to the true Euclidean length. And in the limit, if you have it very densely connected, you can exactly go measure the true Euclidean length of a segmentation. Okay, so this is what you see now here. We have got an 8 connected, and you see here that the segmentation is already better. It's no longer that sharp here, but it's already 8 connected, looks better. But we can go even further. We can actually make this variable here depending on the image, where you have this contrast term. So what this term is doing, it's a high value when the two neighboring pixels have similar colors, and when two neighboring pixels have different colors, has a low value. So you prefer to make a cut where there is an edge in the image, and then this is what you get. So it nicely follows the true edges of the starfish and doesn't cut it off like this here. Okay, so this is quite nice result, and this is what you get here with such, for instance, 8 connected and such a setting of the weights. Then you could go to higher order. This is difficult to optimize. I will later on talk a bit about optimization techniques which can tackle that. But you could, for instance, say, I want to have my segmentation being connected. So you say, for instance, that that this one here is a result of a standard segmentation with these brushes of background and foreground, and here I've got 2 clicks, say that has to be foreground, but it's not connected. And so now you have got a higher order term, like H here, which simply says you pay an infinite penalty if it's not connected, and a 0 penalty if it's connected. And then you get such a result out, which is quite nicely connecting these parts here together. Okay. So this is an introduction of the of graphical models for segmentation. In the second part of my talk, I will go into bioimaging and have quite a lot of, like for 1 hour, I go into details of how to model, for instance, cell tracking, partitioning in connectomics and in other areas, and I will explain much more of these applications and models. For the next hour, I want to go into optimization techniques of these graphical models, which have become quite advanced. There is a study from 2015, from last year, which I'm going to briefly explain here, is comparison of optimization techniques. And it's a nice, pretty big software package where you have already up to 30 or 40 different optimization techniques and a lot of instances. And you can actually use that as a toolbox these days to when you have your own graphical model, to use that toolbox to see which method is the best one. I think it's still good to know what methods are out there and how to tackle it. For instance, later on when I come to the applications, I will use quite a lot of integer linear programs, which you can solve with commercial solvers like Gurobi, but you can also then, we would do for a more advanced one, integer linear program, we will do a very specialized solver called dual decomposition. And so you kind of will see when you can stay with commercial solvers, when you need your own solvers. And this also, this big toolbox called OpenGM, which I will introduce here, you will see what the pros and cons are. So let's go through these optimization techniques. First, let's motivate why it's important to really aim for getting a global minimum, for instance. I mean, you don't need a global minimum, but a low energy is why it's important to really, it's worth to dig into good methods. So this is an application where we've got a sequence of images where the camera moves. And what we need is, what we want to compute is intermediate image between these 2 images. And we can express this as a 4-connected pairwise MRF of a binary labeling. The binary label means if it's 0, it's a certain color. If it's 1, it's another color. There's actually joint work of Andrew Fitzgibbon and Ollie Woodford, and I think Roberto was also involved here. And so let's zoom into this part here. And let's look at so this is the ground truth. This is how the image really looks like. And let's look at different optimizations techniques. So this one is graph cut, and we'll explain that in detail how it works. This one is belief propagation, this one is simulated annealing. And you see that compared to this one, to the ground truth, this one is the reconstructed result. There's some artifact here, this one has an artifact here, and this one has an artifact here. So by applying these techniques, and they're all local minima, they all have different energies, you don't know really, is it a problem of the model or of the optimization? So should I work on the optimization, or should I improve the model of fixing these artifacts here, of getting something which is closer to ground truth? So this one is, by applying a certain set of techniques, this one is the global optimum. And it's quite nice to see this one reconstructed quite well. But what you also see that there are certain highlights which are in the ground truth, which are not in the output result. So one thing you definitely have to put into the model are better highlights. So this was worth to spend effort on making good optimization. And in general, when I talk about this cell tracking, we use, for instance, integer linear programs. We always get global optimality, and that's really important that we know, okay, what's wrong? We have to work on the modeling side, and we don't have to work on the optimization. Okay, so here's a big overview of optimization techniques. And I will explain in the next hour the following set of techniques. So they range from combinatorial optimization techniques like integer linear program to linear programming based techniques called linear programming relaxation techniques, and I explain the two. Then there are also other techniques like QBBO, which is a mix of max flow and linear programming relaxation, so I explain that. I will explain in the second part of the talk dual decomposition and subgraded methods. Then there are methods called message passing, and for instance loopy belief propagation, and I explain that. And then there are so-called move-making methods, which are called alpha expansion or fusion move. And these ones I will also explain. Okay, first of all, it's interesting to say which functions in general can be exactly solved. And there's a lot of research on this. I stopped listing this in like 2010. But there's lots of research in the last 6 years as well, lots of research on which function can be exactly solved and which functions can be solved approximately when they're NP hard. There's still quite some progress here, although for computer vision or medical imaging, I think most of the interesting methods here and here have been done. I think here there's still some advance needed, and I'll come to that a bit later, what's needed. To formalize this, what is a property is functions can be solved exactly if they're so-called submodular functions. And the property of submodular is the following. A pseudo-Boolean function, like a 0-1 function. So I don't do this, I do it on the next slide for many labels. So a binary function with n variables mapped to R, to a real number. So this is our energy minimization problems with n variables mapped to a real number, is submodular if this condition holds. I'm not for all possible sets A and B. I'm not explaining this in detail. I give the constraint for pairwise functions. So for n equal 2, the only constraint which matters is this one here, which is basically for a certain set A and B, like this. And the function is called submodularity condition, which is the following. The function with 0, 1 plus 1, 0 has to be greater equal 1, 1 plus 0, 0. Okay, so this is called submodularity condition, and that's the crucial condition for pairwise function in order to be solved exactly. And we will do the method in detail how to solve it. And then another property is a sum of submodular functions is also submodular. And that's important. Now for our Ising model for segmentation, it's actually submodular, the problem. So it's a sum. So first of all, the unary functions are irrelevant. They can be arbitrary, the unary functions. The pairwise functions are submodular, and it's a sum of submodular functions. Okay, let's see why they are submodular. This condition has to hold. So if it's 0, 1, this is 1, right? 1, 0 is 1. So it's 1 plus 1 is 2 on this side. And on the other side, it's 1, 1 and 0, 0. So it's 0 plus 0. So 2 is greater equal 0. So it's satisfied for each function here. And the sum of these functions is again a submodular function. So our segmentation problem can be solved, is submodular and can be solved exactly. And we'll do the method called GraphCut or MinCut a bit later. Then you can also extend this to multi-label function like pairwise with L labels, and the condition is the following here. It's basically an extension of the binary case, and so you have to pick at label I and label J xi and xi plus 1, and then that condition is that these two cross terms have to be higher than these two terms here. So that's what this condition say. If you plug in xi, xj equals 0, then you get exactly the condition for binary. Okay, so let's start with some of these techniques. Let's start with loopy belief propagation, which can be applied to multi-label, to pairwise function, also higher order functions, but I'm doing the pairwise functions. Okay, so I guess quite a lot of you are familiar with dynamic programming. I'm just going through briefly what that is. So you have, for instance, a chain here, a Markov chain, with some unary potentials on P, some pairwise potentials, which are of the following form. If the label is different between xp, xq, then you pay a penalty. If they're the same, you don't pay a penalty. Okay, so what dynamic programming is doing is computing a message from P to R, and we first compute a message from P to up to Q, and then from Q to up to R, and then we can read out the final solution. So this message here from P to Q has got 3 values. So it's for L1, L2, L3, we've got 3 labels. So let's exactly compute that message. We have got fxp is the unary term, 5, 1, 2 for the 3 labels, L1, L2, L3. And this is node P, and this is node Q. And now we compute, the message says, if I were to choose for node Q L1, what will be my optimal configuration here? And what I do is I simply say, okay, there is the unary term involved and the pairwise term, and I go through all possible configurations and choose the minimum one. Okay? So that means minimum over xp with unary term and pairwise term, which is minimum of, if you choose this label, it's 5 plus 0, because the pairwise term is 0, unary term is 5 plus 0. This one is 1 plus 2, I pay a pairwise term of 2, but the unary term is 1, and the other one is 2 plus 2. So this one here, if you minimize, minimum is 3. So then that means for L1 it's 3, L2 I can compute that, it's 1 the message, and for L3 is 2. And then you can also note with a red arrow which one is the optimal link. So if I were to choose later for Q, node Q, L1, then it's this connection here which is the optimal connection. And also for this one, Right. Now I can compute the next message, which has all the information up to node R. And that means what I have to do is I minimize over Q of all the labels xq. I take the previous message in, I take the unary term of Q, and I take the pairwise term from Q to R. Okay, so that's all the information I have up to this point. And then I do the same thing of marking which ones are the right optimal connections. And then I can read out the final solution. I just minimize over xr of the final node by taking the message in and the unary term of xr. And this gives me then the minimum energy, and I can also trace back the solution. So for instance, this one were to be the minimum, then I can trace it back and I find the optimal configuration. Okay? And that's a global minimum in linear time. Okay, so that can be extended to graphs, to general graphs, and there are many extensions. One is this called TRWS, tree-related message parsing, sequential, which I'm not going to any detail. But one simple one is called loopy belief propagation, where you do the same thing. You compute a message from one node to the next node, and the message takes in all the incoming message in a node, the unary term and the pairwise term. And then what you can simply do is you say, well, I compute messages in a certain order, for instance, in this order here, like first these messages, then these, or I update them in parallel. You also have to initialize the messages. This may not converge, but it's a quite good method, as we see later. In particular, this method called TRWS, which is a certain schedule and a certain way of parsing these messages and formulating a new problem. This is one of the state-of-the-art methods, as we see later. There are also some tricks, for instance, for this message parsing, the number of computations for when you've got many labels here, it's normally L squared, you have to go through all of these possible labels and compute for each of these ones the optimal configuration. So it's like going for all of these ones, and for each one we go for all of these ones. But there's certain tricks. If, for instance, called the Potts model, then it's only linear number of operations. Okay, you can also apply to higher order models where you've got factors and you pass a message from a node to a factor and back from a factor to a node. Okay, so these were the message passing techniques. Let's look at max flow. So who knows max flow min cut? Who knows what that is? Okay, not so many. So I'm explaining now in detail how that works. So we first have to define what is an ST min cut or an ST cut. And then we're coming to how we can minimize energies using ST cut or min cut. So what we're going to define is a graph with vertices and edges and costs. So here we have got always two special nodes, which are called source and sink, and then all the intermediate nodes, which are going to be our variables xi of our problem to be optimized. And we have these vertices, we have edges from source to these interior nodes, and from interior nodes to sink, and also between these nodes. And they also have certain capacity, like 2 and 9 and 2. Okay, so an ST cut is partitioning of all the nodes, interior nodes, that either belong to sink or to source. So we have a cut here, it's called the ST cut, which separates all the nodes which belong to the sink, to the source, and all the nodes belong to the sink. And the cost of that cut is equal to the number of edges which straddle the cut and go from source to sink, go from this set to this set. So in this case, this is 9, 1, and 5. So it's 15, the value of this cut. The value of this cut here is 2, 2, and 4, which is 8. So this transitioning from here, the value is 8. And there are other cuts, like this cut up here and this cut here. Okay, right. So then what is an ST min cut? An ST min cut is the ST cut with minimum value. In this case, actually 8 is the minimum value. If we see later when you cut up here, cut down here, it has a higher value. Okay, so what has this to do with energy minimization? What you're going to do is we formalize a graph such that any ST cut corresponds to an assignment of x, and the cost of the ST cut is equal to the energy E of x. Okay, so I explained that in detail. So we have an energy, and when we take these unary and pairwise terms and put them on these edges here, with connecting these between the connections here between the nodes and also between these nodes. And what I now do is any ST cut here, I define a labeling in the following way. If this is the cut, I say all the nodes which belong to source have got labeled 0. All the nodes which belong to sink have got labeled 1. Okay? Now what I have to make sure is that when I've got this assignment here, that the value of this cut here, of this ST cut, the value is the same as the energy of this particular configuration. And then if we have this property, we can simplify the minimum cut, which is this ST cut with minimum value, and then I can read out the minimum energy or the configuration because we know they correspond. In the following, we have to assume that it's submodular, and in a few minutes we extend this to non-submodular. Okay, so the first thing we have to do in order to do this writing, we have to do so-called reparametrization. We have to change this energy into this form. If it's submodular, this can always be done. And the next 5 slides are showing exactly the transformation, but I'm not going through this. You can later on the slides, when you see them, you can exactly go through if you want. So what we do is we change the unary terms in the way that we have sum over I pixels, ci, xi, plus ci dash 1 minus xi. And the ci and ci dash are always greater or equal to 0. And we also, the arbitrary unary terms here, for instance, for if it's binary, you've got 4 possible entries. You change it in this form here. Yet you have always the form Cij and xi 1 minus xj. Okay, and the Cij are also greater or equal to 0 if it's submodular. Okay, so you can always do this conversion, and here this is extra material for you later to study if you want, where you have these transformations. Just one hint, basically what it boils down to is that you move some of these, like for instance interior terms here, like theta 1, 2 with 0, 1 labeling, you move that down here to this node, and you change the unary term and you change pairwise terms. It's called reparameterization, but I'm not doing this. Okay, so let's assume, just going back, what we've been doing is we are able to convert this one into this form here. Now what we're doing is we have here an energy in that form, and we now simply put all of these weights here into the graph. Okay? So what we're doing is we take node V1, and if it's V1, we have the 2 we put into from source to V1. If it's 1 minus V1, we put the 5 from V1 to sink. For the V2, we do the same. For V2, we have first a 9, and that's up here, and a 4, and that's 1 minus V2, which comes down here. V1, 1 minus V2, that's a link going from V2 to V1. We put a 2 in here, and it's a 1, and for this one here, we go the other way around. So this is simply a way of writing these numbers into this graph. And now, by construction, I show that it's exactly doing the right thing. Let's go for all possible cuts and see that the energy is identical to the minimum cut. So if the cut, ST cut, were to go through here, through here, then you cast here 2 and 9, which is the ST cut is 11. Now let's see that we want to have the labeling because these two nodes belong to sync. Labeling is 1 and 1. Now we plug it in. So it's 2 plus, this is 0, this is 1, 2 plus 9 is already 11. This one is 0 here, this is 0, and this is also 0. So it's 2 plus 9 is 11. And you can do this for the other ones as well. You can have the cut going through here. You see the ST cut, the variable 0, 0, and the value of the ST cut is the same as the value of the energy. Okay, you can have another cut here and another cut here. And then by going, I mean there are only 4 possible cuts. By going through, you actually see that 8 is the minimum cut and is also the minimum energy, and the configuration is 1 and 0. Okay, so how can we use this now? We want to compute this ST min cut. What we want to do is or what we can use here is this min cut max flow theorem, which says that in every network, the maximum flow is equal to the cost of the minimum cut. So now we're solving another problem called the maximum flow problem, and from this one we can read out the ST min cut, and from that we can read out the final labeling. So how do we solve this maximum flow problem? What we do is you can think about these edges here as pipes with a certain capacity, like this capacity 2 or capacity 9, and this capacity 1 and 2. So you can think about is you push water through this network, and network goes through here. This is a pipe with big capacity, this is with small capacity. And then we push the water through, it goes into sink, and we push as much water through as possible. And once we push the maximum amount of water through, there are certain edges which are saturated. And the ones which are saturated, these are the ones where the ST min cut goes through. So we push all maximum water through, find the saturated edges, and then this gives you the cut. Okay, there's a huge history on min cut or on max flow algorithms going from augmented path to push relabel, and here's just a long list of methods. Practically in computer vision or bioimaging, what I'm doing, we use a lot of technique from 2004, which doesn't have the best complexity, but it's empirically good one, because the unary terms are often highly correlated, and then it's a very specific search tree, like augmenting path algorithm with clever search trees. Okay, so let's do one augmenting path-based algorithm. The flow initial flow is 0, and we now have to push as much flow as possible through from source to sink. So how does this work? We have to find an augmenting path. That means a path from source to sink where there's still capacity to push water through. So here's one with this capacity 2 and 5, and we can push units 2 through this network. We cannot push 5 because this has only capacity 2. So let's push a flow of 2 through here, and then this one is residual capacity 0, and this residual capacity 3. Now we can try to find another augmenting path and try to push more water through. So let's take this one here. This one you can push water of 4 units through because this one has capacity 4. Okay, so let's do this. We increase the flow to 6, and this 5, this is 0. So let's look for one more augmenting path, which actually is here 5, and then we go here 2 and 3. We can push 2 through this path here. So let's do this, push 2 through, and we get a flow of 8. And now we've reached the maximum. We cannot push anything here. We can go here, but then we can't push any further here. So this is the optimal configuration. And this is exactly what we wanted. So we've got flow 8. These are the saturated edges. And it's exactly, this is the optimal labeling. We've got this one, V1 is 1, and this V2 is 0. And we can read out the optimal configuration and get the energy of 8. And this is also flow of 8. Okay. Now I've explained max flow. So what do we do with non-submodular, which happens in practice also quite often, and we have later some examples of it. There's a certain technique called quadratic pseudo-Boolean optimization, which deals with non-submodular problems. So I'm just explaining you the main trick of this. So what you do is you can take your energy and write it with unit terms, with pairwise terms, which are all the submodular ones, and we denote all the ones which are non-submodular with a tilde. So we have theta tilde of all the pairwise terms which are non-submodular. Okay? Now the idea is that we relax the problem by doubling the number of variables. So here this is the energy with with submodular and non-submodular. And now we write a new energy, E dash, where we double the number of variables, where we've got xp and xp bar. And we simply write this energy here. So what does this mean now? We can, if xp bar is equal to 1 minus xp, if this condition holds, then E is equal to E dash. So we put in, let's check this, we put xp bar, we put that in here, 1 minus xp. So it's 1 minus xp, so it's 1 cancelled out, minus cancel out, so it's theta p xp plus theta p xp is 2 times, divided by 2 is just theta xp, which is exactly here. That is actually part of a global optimal. So any pixel which is labeled is part of a global optimal. And there's some extension to it which I don't want to talk much about. So here's an example for our problem with these, of the leaf here, of this guessing what is the true color. This is typically what happens. So you get some pixels labeled, and these black pixels have a question mark. They're not labeled. And this one is what GraphCut gives you. Okay. Now come to a quite important set of techniques which we use a lot in bioimaging. And this is called integer linear program and linear program relaxations. So linear program relaxation approaches work as follows. You write your energy minimization program as an integer linear program, and then you either use commercial solvers such as Gurobi, which I'm showing later, which we use quite a lot, or you solve a linear programming. Use a linear program solver. That means you take your integer linear program, relax it to a linear program, solve the linear program, and then round the solution. For instance, to the closest integer solution. Okay. So how is this done? We write the energy minimization in a different form where we have so-called indicator variables. We have so XPA and XPQAB. For instance, if XP is labeled 2 for 3 labels, 0, 1, 2, if XP is labeled 2, you have an indicator variable saying that, okay, XP2 is 1 and all the others are 0. So it's exactly saying, okay, this configuration has got labeled 1 because that's a true configuration, and the other 2 have labeled 0. Right. So this is an indicator variable saying which configuration is on. And now we can write all of our unary and pairwise terms in this form here with these indicator variables. Additionally, we have, so this is the called objective function, we have constraints of equality or inequality. And these constraints here will make sure that it's a valid configuration. For one thing, for instance, we have to sum over all possible A, and we have to say that these ones are equal 1. That means we can only have one of these ones switched on. Either it's labeled 2, or labeled 1, or labeled 0. Another ones are called so-called marginalization constraints. We are making sure that when this label is on, XP0 is for instance switched on, then either this one or this one must be switched on, because this P, that should be P here, because the P has to be 0, right? It should be P has to be 0, P has to be 0. It can't be this switched on, right? Because then P would be 1, and that's not correct. So we're summing over all these incoming links and have to make sure that they're equal to this one. It's called marginalization constraints. And now what we're doing, we can relax it. We simply say that it doesn't have to be in a set 0, 1. We just say it's greater equal 0. And then we can solve it with commercial solvers or other solvers. This linear program can be solved exactly. And then we round the solution, for instance, to the closest integer. Okay, so here's an example where you see that you need this rounding. So this is an example with PQR with 3 nodes and always 0, 1 labeling. There are no unit terms, and the pairwise terms is that for all these pairwise terms here, we say if you have a different labeling, you pay -1, so you like it. If it's the same, you pay a 0. Okay. So the optimal value is -2. There are many possible labelings. There's like, for instance, 0, 1, 1. Could also be 0, 0, 1. You at least some different labelings. So this one here, because these are different, you pay -1. These are the same, you pay 0, but these you pay -1. But you can't have -3 because you must choose, you can't choose a 2 here because you only have labeled 0 and 1. Okay. So in our configuration, what we draw before, you've got these XPQ00 and P0. So this one is 1, this one is 0. So this one is drawing it as before with these cross diagrams. And the value is -2 if you draw this. So this edge here has got a value of -1, and you multiply it with 1. That's called the map solution. If you relax it as another solution, it's got value -3. You can actually put all of these ones here 0.5, and then you pay 6 times these pairwise terms with -1 of value 0.5, and then you get -0.5 times 6 is -3. And these ones satisfy all the constraint. So the sum of these two is 1, and the sum of the incoming links is the same as here. So 0 plus 0.5 is 0.5. Okay, so for this one you see you need you have to round it or do something with it. Okay, so let's starting to round it up. So these are the 2 last techniques I'm explaining. It's called alpha expansion and alpha fusion. So these are move-making methods. What are move-making methods? These are methods where you look at a certain search space. So you have your current solution. You have a certain search space, and within the search space you do an optimal move, and then when you've done the optimal move, you look at a new search space and try to do the next move. So here we're doing this, have this search space, we're doing the optimal move, which is then to this point. And now we do a new search radius, and we tried an optimal point, and so on. And in this case, we were lucky to get the optimum. If the search space is very small, if it's very small, you could deteriorate and go down here. Okay, so I'm just discussing one, which is graph cut-based move-making methods, called alpha expansion, which has got a quite big move space of the form that so L is the number of labels, so the whole solution space is L in the power n when you've got n variables, and this search space is 2 in the power n. So we always look at 2 in the power n search space, find the optimal move there, and then have a different search space. So how does this work? Alpha expansion is a pretty simple technique. You have, for instance, here you have got 4 labels. You want to find the optimal configuration. You initialize with a certain labeling called tree. So you initialize everything with one label, tree. And then you expand with ground. That means you either keep tree or have a new label called ground. Okay, and that is here you have expanded to ground. And the next expansion is with this yellow label. And again, it's a binary problem. You either keep the labeling or expand to house, to yellow. So that means here you either, for these pixels here, I chose yellow, the other ones keep the labeling. You cannot, in this move, you cannot transition between tree and ground. You can only keep this or have this one. And then you can expand with ground. You keep this or you expand with sky, sorry. So this is called alpha expansion, and here's formally the algorithm written down. You initialize with a certain labeling. You then go through all possible labels, 1 to k. You construct a so-called binary move energy with binary labels. You check if it's submodular. If not, you can do kinds of trick, truncate it, you change it to make it submodular, or you apply QBBO in the next step. So then you apply QBO or graph cut to this energy, and then you read out, you update the original labeling depending on what this energy E dash is doing. So if it's 0, you do nothing. If it's 1, you change it to the new label. And then you can repeat this. Go to step 1. If the energy doesn't change significantly, then you go back. Otherwise, you don't go back. And here, just for you later to check, this is exactly the move energy. Okay. There's a certain condition when you can apply this called, it has to be matrix. Basically, this inequality has to hold that for pairwise terms LA, LB, and LB, LC, this has to be greater to LA, LC. And this is satisfied for Potts model. Okay, there's another extension, and I think Ben Glocker in his later talk will use this quite frequently, called fusion move. The idea here is that you not expand with a certain label, but you expand with 2 arbitrary solutions, can even be continuous solutions. For instance, for optic flow, you compute the motion in the image. Then you've got here the continuous solution. Here's another continuous solution. And you have a binary decision which ones you want to take. You write this down as going from the original continuous solution. You can write down this discrete problem. Then you solve it exactly, hopefully, with QBBO or graph cut, and then you can update your it by taking for 1, you take this solution here, and if it's 0, you take this solution. Okay, and so this T is this kind of decision variable what solution to take. Okay, so that was a very quick quick way of going through various techniques, touching on all the essential ones from combinatorial optimization to message passing to max flow-based techniques. And now let's look at some comparison. So there are quite some studies, and the most recent one is called, on the software package called Open Graphical Models from Jörg Kappes and others from Heidelberg. There are also more recent, more older studies. I will just show you briefly some of these results from these studies. Here, for instance, this is on stereo matching. You run all of these techniques, and for this particular example, you see, okay, alpha expansion is really good, and then also the TRWS is actually pretty good. And also this one here, which is, I think, this loopy belief propagation. But for another example, for instance, TRWS, which is a message passing technique, is really good, and alpha expansion is slightly worse. One other thing, when you've got very continuous labels, for instance, for denoising or in-painting, you see that message passing techniques like TRWS give much better results than alpha expansion, because alpha expansion always expands with one label, and this can give you quite discrete transitions here. So some conclusions is that alpha expansion and TRWS are the best methods for connected and densely connected or large images connected. And alpha expansion has problems with smooth areas. So this one here is the most recent study from using OpenGM. It's a software package, very good interface, has got 32 state-of-the-art methods and 2,200 problems, ranging from medical imaging to hard problems, small problems which are very densely connected, to cell tracking by assignment. And I will talk in my next talk in detail about how to do tracking by assignment, partitioning problems, or pixel problems where you could do pixel-wise labeling, or superpixels. And so this is a big overview of what the current status is. It's sorted here by the number of the problem size, so the number of variables. Green means that these problems can be solved optimally. For these ones here, sometimes can be solved optimally, that for some instances you solve it optimally, for others not. And this one here, no instance can be solved optimally. So obviously, as expected, the more you go up here, the bigger the problem is. Also, one important thing is how densely connected it is. But the bigger the problem and more densely connected, you get more yellow and red. For lower ones, you get a lot of green. So this is kind of all solved here. Then certainly, obviously noticeable is that pixel-based methods have more variables, are more densely connected as well, compared to superpixel-based methods. And so these ones, pixel-based methods, always are at this end here with bigger problem size and are more difficult. So in general, the summary for this study is that medium-sized problems up to 2,000 or 5,000 variables and sparse connectivity, exact solvers, even commercial solvers such as Gorobi, are very tractable and sometimes faster and better than approximate methods. For large-scale problems, the exact methods such as ILP solvers are no longer tractable in a naive way, and efficient approximate techniques such as alpha expansion are still interesting. So here's an example of geometric context. You try to say each pixel, is it ground, or which direction is it facing, or is it sky? And you see here all these solvers, and you see that OpenGM alpha fusion move techniques is pretty fast and gives you pretty in average good energy. But there's actually an ILP solver, commercial one, which is slightly slower and gives you even lower energies. So here, this is a problem. There are like up to 1,000 variables where there's a competition between these two techniques. Okay, so the last 10 minutes I will spend on, let's see what the time is, yes. Last 10 minutes I will spend on my personal view of comparing neural networks and graphical models. When you meet, like these days there's so much on deep learning and convolutional neural networks, people say, do we need at all graphical models? And I think it's worth it's worth to understand that a bit more closely and see what are the pros and cons and what can the two worlds learn from each other and where there are interesting research directions. So on one end we have these convolutional neural networks where you've got, for instance, an image, and you can give out even a dense labeling. You either give out a number or you can give out a dense labeling. This could be convolutional neural network or stacked random forest. And these are convolutions, and they're all learned. All these features are learned, and they're very powerful. We get very good results, also quite smooth already, the output. On the other end, what we discussed are undirected graphical models. And I think one of the main benefits, what I want to come to, is that add explicit prior knowledge, such as cell division or image formation process, and I will give examples of this. That's very useful when you have explicit prior knowledge. That's very useful to use directed graphical models, ideally in conjunction with convolutional neural networks. So here I have 3 recent pieces of work where I talk about the combination of these two, where I want to address this explicit prior knowledge in more detail. So the first one is without prior knowledge, is a general combination of CNNs and generic MRFs. There's also Raquel Utunsan, she will talk about deep structured models, which will be a very detailed perspective of this. Then I'm going to have 2 examples. One is spine detection with stacked regression trees, and also comparison to CNN. And the other one is image denoising with, decision trees with stacked regression trees. So this image denoising and spine detection are examples where graphical models are needed in combination with these feed-forward models. Okay, so generically what you can do is you have, let's say you have a CNN, and a lot of these papers which do the following. They have a CNN that gives you the unary potential, and then you have pairwise terms which give you which then could do some extra smoothing on top here, and we will see that in a second what are results of such a method. So you have these ones as unit terms, and additionally you have got quite arbitrary pairwise terms, theta ij. Ideally you want to learn all of them jointly, and I think Raquel will go into details here. I cite a paper we've done last year where we jointly train all of the convolutions here and all of the pairwise terms here. So all of the parameters, all of these ones and these ones are trained jointly. And there are several papers in this direction. Ours is actually a paper which scales pretty well when you have got large graphs. Okay, so what do you see here? This is an example where you want to label body parts, and actually we use the same techniques for labeling, for instance, a zebrafish or human spine, the different vertebrae in the spine, and I'll come to that in a second. So you want to label different body parts of this in this Connect image. Now, this is what the CNN is doing when you train separately. So the CNN is trying its best job. It's got an accuracy of 84.5%. And also it's very certain, and means trying to be as certain as possible about the right labeling. But there's a bit of uncertainty, it could be other labelings, but it's quite certain about this. Then you train this separately, you put an MRF on top, and it's smoothing it a bit out. You get like 3% improvement roughly. So it's smoothing this out, but it's not the optimal solution, like this should be this label here. Okay? So it's smoothing it out. For instance, this edge here is also smoothed out. When you train it jointly, it's interesting. First of all, the overall result is slightly better, so it's 1.4% better. Additionally, it's interesting to look at what the CNN has been doing. So the CNN is far less certain about what is the right labeling. It gives you much bigger distribution of possible labelings. So here as well, the true labeling is in there, but it's also another labeling is just slightly more likely. So the CNN has been learned to be more careful and not committing to one label, but being more careful. And the hard work has been taken over by the graphical model. Having said that, we also compare that paper to a specialized CNN. So there are papers, and I think Raquel will go into detail, there are papers where you say, well, actually what you can do a certain inference called mean field inference, which I haven't discussed that. So it's mean field inference of these graphical models, and a mean field inference is just applying a set of convolutions. So you say, well, in the inference here, you can say I just do 20 convolutions, which basically means a certain fixed fixed time length of this mean field inference. So instead of having a graphical model, you say the inference of the graphical model is basically a CNN, or recurrent neural network, and you just have then a general CNN plus a recurrent neural network additionally just plugged together, and this network, where the filter weights can be learned as well, is mimicking the inference of a graphical model. And when you do this, you get 88.2%, which is pretty close to 89%. So here this is where it's getting interesting. So graphical models can help to motivate better CNNs for doing inference, which doing similar things to Markov Random Fields. But here it's very blurry boundary. There's no explicit prior knowledge here. Just to visualize, so what these terms have been doing, they can actually learn being smart in the sense of what should be next to what. So this is left torso, right torso. The center pixel has label left torso, and the pairwise term to the neighborhood pixel for right torso. So these are the 64 possible pairwise terms. So it's kind of like densely connected here and more wider connected. And what you see is that it prefers that the center pixel, left torso, the right torso is more likely to the right of the left torso, which makes sense, left torso, right torso. So this is encouraged. These are negative small weights, and it's discouraged that it's on top or below. Ideally, it should also be discouraged here, but that's actually not needed, because when you learn it, the CNN would never get it wrong. He would never swap the left and right torso, so you don't really need strong weights here for the CRF. But you need these weights here to clean it up. Okay, so now I'll give two more examples where we have explicit prior knowledge using CRFs in combination with feed-forward models. So the first one we used here is spine detection of a zebrafish. So we have an image of a zebrafish. We have a random forest or decision tree, so stack decision tree, which says for each pixel what vertebra could it be. Like vertebra number 20 is, for instance, more likely down here. Then we have an explicit graphical model which fits a spine to the zebrafish. And also we have an active appearance model for the shape of each of the vertebra. So this one is quite explicit prior knowledge putting in. We fit this here, and then we plug it into another random forest, and then we have this as output plus the original image, and we get a better prediction of the vertebra, and again we do a spine fitting. So actually in this work that was last year an oral at MICAI, we went a step further by not only looking at the inference, not only looking at the map inference, but also at the marginals. So here you see the different stacks here. Actually there are 3 stacks. It's like after fitting 1, 2, and another third, and then output. If you do the map solution, you can get stuck in the first level with a certain result, and you never recover from it. It's kind of staying with that result, and this is the true result. It should have been a different vertebra. If you do marginals, meaning uncertainty, the different levels later can use this uncertainty to recover the true position. So here it says the most likely position is the wrong one, but also this up here is a bit likely, and also down here is a bit likely, and then the next levels of the stack can recover from it. So here are like 3 iterations, level 1, level 2, level 3, and you see that this kind of recovers. So this is the true position of this vertebra, and this is the true position here. And so you see this one going up here over the levels. Okay? And now it's interesting, we just have a BMVC oral paper accepted where we compared this to a CNN. So what we've been doing is we take this pipeline, but we don't have this here, and we take these stacked random forests. We can make an exact mapping to a CNN, and then we initialize that CNN and train it further, the CNN, and we also get labels out, and we are slightly worse than doing this explicit procedure here. So a CNN is slightly worse than this procedure, but the next step is obviously to replace these random forests with CNNs, and then I think this procedure will be even better. So it's not a definite answer to say this is much, much better than this one here, but right now it's already slightly better, but if we replace here CNNs, this will be, I think, considerably better, because you put this prior knowledge in. This work was mainly about how to initialize CNNs in a smart way when you have got, for instance, stacked random forests, which are more robust, especially when there's little amount of training data. With little training data, it's easier to train stacked random forest than a CNN, and training CNN from scratch is harder when you've got little data. That was the main purpose of this paper. Okay, here's a video. It doesn't play. Just a second. So this is a spine here where you see the positions of the spine is a bit hard to see, but over the levels it recovers to the true position. I'm just playing the video here. So you see these points here. The white one is a true spine moving close to the true positions. For some reason, when I play it in the online view, it's not working properly. Okay, so last paper I want to mention also with this explicit knowledge is the following. We want to do deconvolution, and we have an image and the blur kernel, a known blur kernel, and want to deblur it. So this paper actually was won the best student award at CVPR 30. So this is what we've been doing, is we do a stacked model where we have the input image, then we do, in this case we did regression trees. That was 2013 before CNNs. So we did regression trees to regress a possible labeling here. And then we have a Gaussian CRF, a generic Gaussian CRF to clean it up. And then we take the output into another level of a regression tree and so on. And we do typically 3 or 4 levels. Now this is a generic Gaussian CRF. We have got certain thetas here of this term and thetas here. So this one is the mean and this is the covariance of this distribution. So we train all of these ones in this way. And one option could be that we train for each possible blur kernel, we train this stacking here. But that would be not very good, right? For each possible blur kernel, it would be a different method, which is insane in a sense. And there are also a huge number of possible blur kernels, like close to infinite number of blur kernels. So now what we've been doing is we use prior knowledge to make this more smart. I'm not going through much of the equations, but what's happening is the following. We can write down the image formation process, which says that we take the output, convolve with its k, and add Gaussian noise, and that is the true image z. That's the input. So that's the input image z. Take blur kernel, take the output, convolve with k, add Gaussian noise, and this is for the posterior for distribution over z given x. Right? This is for the likelihood here. Now, it's quite nice. So this one is a Gaussian, and this one is also Gaussian. And now we can add the 2 Gaussians together and get a new Gaussian model, which has generic parameters, but also parameters which come directly from the blur kernel. And now this process suddenly is much better, because this process now, these terms you only have to learn the mistakes of what is not already recovered by the blur kernel. The blur kernel already can deblur it, and then you only add the mistakes here, it's more denoising, with this generic model. Okay, and then we actually got state-of-the-art technique, which is slightly better than state-of-the-art, but much faster than state-of-the-art. Okay, so that was the introduction to graphical models. I hope you found it interesting. So I tried to give a quite big overview of optimization techniques, quick introduction graphical models with segmentation, talked about comparison of all of these techniques, and then have my personal view of neural networks and graphical model. And then next we do a quick break of probably 5 or 10 minutes. How long is the break? Yeah, like 5 minutes or short break. And then I talk about using all of these optimization techniques for bioimaging. Okay, thank you.